Okay, a second way I've used interpolation is I wanted to look at minimizing a swim time for a given distance. Let's see, by using pace strategy. So, should I go out fast? Should I go out slow and try to speed up? What should I do? What strategy would give me the quickest time? And let's see, I think I need to pause it here for a second. Now, in this case, so what we're saying is we wanted to minimize, say, time, t, but we had some constraints, so subject to, well, we had to cover the distance. But, what's the distance? Well, it's the integral from 0 to the end of our race, the time there, of our velocity, or our pace. Okay, so we had that. In our pace, we probably shouldn't go backwards. So, we wanted the pace to be greater than or equal to 0. But then what else? Well, we ended up in this particular model, what we said was at any given time t, our pace, our speed, had to be less than or equal to some maximum speed, but then minus some sort of energy thing. And that's where I won't really go into much detail right at the moment here, but, for, how hard was I working for some amount of time? So, that might be up to the current time, and then, some delta t before that, t minus delta t. And, this was some sort of unknown function of the pace. And so it's a pretty simple model. I mean, in the sense that there's not much here. There's minimize the t, and there's this integral here, and so forth. Well, the thing is, what we don't know is that velocity as a function of time. Well, and if you look at that, I don't know about you all, but I do not know how to solve this problem. I mean, I know some ways you would look at it, but in the end, I'm not going to get a solution. This looks really, really hard. However, the way we could use interpolation was, if I have a function, so this is just sort of a theory thing, but if I have a function, say v of t, but now I just pick certain points on it. Now, I have no idea what the heck that function is. But if I assume some particular points on it where I don't actually know their values, but my interpolation is that, I think that by going through those points, and we'll learn this in the interpolation, say I could have a polynomial. These are 5 points. I could have a 4th degree polynomial. So I could have ax to the 4th plus bx cubed plus cx squared plus dx plus e, not to be confused with the number e. Now, I don't know a, b, c, and d either, but the key here is that notice with this integral, let's just, look at something like this. I've got the integral from 0 to t of v of t dt, or I could say, well, that's approximately, and we'll just use the ax to the fourth, that's approximately equal to some a t to the fourth dt from 0 to t. Well, I can do this integral. That's just a times t to the fifth, big T to the fifth over 5. Well, see, so what I gained by thinking of an interpolant here instead of the actual function is now I have an algebraic equation because I've just got, a t to the fifth over 5 equals d. That's an algebraic equation instead of an integral equation. Ooh, easier. Okay, so that is another way I've used interpolants, is to change a really horrific, nasty model into something that at least is a little easier to deal with. In this case, algebraic equations instead of all this unknown integral stuff. Okay, so that's another way I've used interpolants. And so they're just, we're going to learn about interpolation and kind of look at a couple of these ideas, just so if you were to need to use something like interpolation to either represent a structure or to help you transform a harder model into an easier one to solve mathematically, we just want you to see that tool because it's a very nice tool. Okay, call that one done.